Okay, Calculus, here's your first lesson of the day, Undercover. You have just taken over as manager of a struggling umbrella company. Umbrellas are manufactured at a rate given by G of T equals 20T minus T squared umbrellas per hour for hours 0 to 14, and T represents the hours after the factory is opened in the morning at 6 a.m. G of T is graphed, as you can see below, and that's also on your paper. So let's move down. After a leisurely breakfast, you arrive at work at 9 a.m., so 3 hours after you have opened. Write an expression that gives the number of umbrellas that have been produced before you arrived. Well, this is our accumulation function, G of T, so if we're looking for the number of umbrellas that have been produced, that would be the number of umbrellas produced from hours 0 to 3, G of T dt. So we're going to take the integral of our accumulation function for the hours from 0 to 3. Roughly how many umbrellas were produced during that time? Well, you pick your favorite way to estimate this. Obviously, you could use a left or right Riemann sum, maybe a midpoint Riemann sum. I'm going to use a trapezoidal sum here. So I'm going to use G of 3 plus G of 0 divided by 2 multiplied by the width of my interval, which is 3. Well, G of 0 would be 0 umbrellas produced when we open. G of 3, well, you got to plug 3 into your equation up above, and that was 20 times 3 minus 3 squared. And then, of course, divided by 2 multiplied by 3. Well, 20 times 3, that's 60, minus 9, that's 51 over 2. Times 3, which is 76.5, or approximately 77 umbrellas. So 77 approximately umbrellas produced in those first 3 hours that we've been working. At 12:30 p.m. you break for a long lunch. Write an expression that gives the number of umbrellas that have been produced that day up until your lunch break. Well, if we open at 6 a.m., how many hours have we been open? Well, we're looking at 12:30. So the number of umbrellas produced from 6 a.m. to 12:30 p.m. would be the integral from 0 to 6.5, 6.5 hours pass in that time interval of G of T, and then of course dt. Now, roughly, how many umbrellas were produced during that time? Well, thankfully, if you think about it, we've already done if this is 3 here, let's see if I can get a 3 in between the 2 and the 4. So this is 3, and we've already used our trapezoidal rule. Let's see, we'll drop a perpendicular here. And then this is the estimated area that we calculated earlier that gave us the accumulation of umbrellas from hours 0 to 3, but now we want to calculate from 0 to 6.5. So we're looking for this volume, if you will, this area under the curve, or volume of umbrellas, accumulation of umbrellas. We need to add to the initial that we had. We need to add this area under the curve here. So I'm not going to color that completely in, but that's the area under the curve we're trying to calculate. So the cool thing is we already have this area from 0 to 3. We're now just going to calculate the area in addition to that from 3 to 6.5. So how many umbrellas were produced? Well, we have 76.5 that were produced already from hours 6 a.m. to 9 a.m. plus we need to calculate the umbrellas generated from G of 3 to G of 6.5. I'm going to use the trapezoidal rule again. So I'm going to divide that by 2, and then I'm going to multiply that by the width of that time interval, which is 3.5. I'm going to let you calculate those values. I'm going to go ahead and tell you that it ends up being approximately, actually I think it's equal to 319 umbrellas. And you say, well, where did those numbers come from? Well, go in, substitute 3 into your function up above, the 20t minus t squared, and then plug in your 6.5 into the 20t minus t squared. Divide by 2 after you sum them, and then multiply by 3.5. And then, of course, add your 76.5, you'll get 319 umbrellas. So in the first 6.5 hours that company's open, produce 319 umbrellas, okay? And keep in mind, this is an accumulation function. So we're looking at our rate of change, and then we're summing the areas. That gives us how many umbrellas have been produced. Now, write an equation for the integral for a function f of x. That gives the number of umbrellas produced x hours after the factory is open. So f of x equals, well, again, we're looking at the accumulation here. So from 0 to x of what? Well, of my function g of t dt. This is my accumulation function from 0 to some hours x. And that we're calling that f of x, okay? Now, find f prime of 8, all right, and interpret your answer in the context of this problem. Well, f prime of 8, when you think about it, if I take the derivative of this here, well, the derivative, I've hinted at that before, undoes integration. So really I'm just left with g of 8, or g of t. Well, f prime of 8 is really just g of 8. And well, g of 8, well, that's 20 times 8 minus 8 squared. And what is that? Well, that's 96 umbrellas. But what are my units? It's not 96 umbrellas because we're looking at the rate of change here is umbrellas per hour. So we're producing at 8 hours after we've been open. So I guess that's what, 4 p.m. because not 4 p.m., 2 p.m. It's 8 hours after we open. So we open at 6 a.m. This is 8 hours later. Our rate of change, our rate of increase in accumulation of umbrellas is 96 umbrellas per hour. F prime of 8, this is the rate of change of umbrellas. And this is a big deal here. We're looking at our accumulation function, and we're putting it in terms of f of x. And then when we take the derivative, we're looking at our rate of change per hour, which, by the way, is g of t. All right, so now when is f of x changing the fastest? And how do you know? Well, let's go back and look just kind of simply at our graph. Remember, this is a rate of change graph right here. This is our rate of change. When is our rate of change the fastest? Well, where's the peak? Simply, I think the peak's right here at 10 hours. This is when our rate of change is the greatest. It's about 100 umbrellas per hour. So at t equals 10, that's when f of x is changing the fastest. That's when our f prime is the greatest, and that's at 4 p.m. I must have been predicting that earlier. 4 p.m. Because the rate of change, the ROC, is the greatest at that time. I'll just say the greatest at that time. And it's about 100 umbrellas per hour. What is this, by the way? This is a maximum. And what is it a maximum for? It's a maximum for f prime of x. It's also g prime of t. Those are the same, right? It's where f prime of x or g prime of t is at a maximum. Okay? And keep in mind that the derivative, what we're talking about here is the derivative of f of x is g of t. Or better yet, g of x. Okay? So keep in mind, and don't let all this confuse you, but f of x is the integral from 0 to x of g of t. When we take the derivative of both sides of this, not only we're getting f prime of x, but we're getting g of whatever that x value is, or whatever that t value is. And let me just write an example of this. For instance, f prime of 8 is equal to the accumulation function at that time. Okay, so this is showing us our rate of change, and we're relating this function that when we find the area under the curve, we get the accumulation of umbrellas. But when we look at just any particular point in time, we're looking at the rate of change at that point in time. Okay. Summarizing some of this, I've got your notes right here. An accumulation function outputs the area under a curve from some starting value to x, the input. So here you see capital F of x equals the integral from some starting value to x of lowercase f of t dt. This is the rate of accumulation, okay? So when we take this integral from some starting value to x, we actually get the accumulation because we're finding the sum of this accumulation function, this rate of accumulation. And so this brings us to our fundamental theorem of calculus, part 1 that is. The rate of change of an accumulation function, the derivative of that integral is equal to the derivative of capital F of x, which is equal to f of x. This is a big, big deal, and we're going to talk more about this in class. But this is our fundamental theorem of calculus, part 1. And this really brings us to some properties of integrals in our next lesson. What I'd like you to do in class is work together to look at these notes and look at what I've recorded before, and then try to answer some of these questions down here. See where you get. I'll send out some solutions. But try to apply not only this idea here, but then our fundamental theorem of calculus, that the rate of change of an accumulation function here, we've got this picture where we've got the derivative of the integral equals the derivative of capital F of x, which is equal to lowercase f of x. And we're going to look at this in class some more, but go ahead and work together, and then we'll look at this together when I get back on Tuesday.